over the years. So Cliff, thank you.
Well, thanks. Thank you for that very kind and flattering introduction. I don't have any slides, so we can enjoy the NSF logo for a change of pace. I want to comment on a whole range of things here. I don't have sort of a neat narrative that takes us to one conclusion, but I want to reflect on a few things that I've heard over the past day of conversations. I want to try and connect this up to some conversations that are going on in other areas, and hopefully both underscore some of what I see as the key issues that have already emerged and put a few extra ones on the table as well. And I'm not going to be shy about being opinionated here. So I think the first thing that we need to grapple with is what the sort of scope and nature of software for cyber infrastructure really is. And I think we've been very nebulous on that point, and at the same time we seem to be sort of creeping up on a taxonomic understanding of it, if you will, and I think it would be very valuable to put some effort into codifying that taxonomy so that we understand where we sit. It's clear that there is a bunch of stuff that I would really characterize as middleware and building up from middleware. It's stuff that serves a range of disciplines, a range of institutions. Often it is very neutral as to specific scholarly practice or methodology, and I think it lends itself to being recognized and procured as sort of serious production grade software. Although we don't always have good mechanisms to do that sort of procurement and management within our funding agencies. And I was very much taken by the discussion yesterday about thinking about at least that class of software a lot like procuring other kinds of major experimental apparatus, and with the same kind of discipline and attention to qualifications of producers and expected life cycle and other kinds of things. Over and above that, there is this sort of collection of maybe it's research software that lives within the cyber infrastructure context. Maybe it's cyber infrastructure software that's discipline specific. There's a continuum in there we don't really understand, and where there's a fair amount of dynamism actually. As somebody develops something, it proves to be valuable, it builds up usage, it starts jumping from one organization or one group of scholars to the next. It may actually even see some reuse or repurposing in various contexts. That's probably the most difficult area to deal with, but also perhaps the most important, because that's where unpredictable kinds of innovation are likely to be emerging. I'd suggest that we don't want to over-engineer in that area. I think it's very dangerous to over-engineer in that area. It could prove to be a real barrier to progress. I think that we may really want to consciously accept some suboptimality, perhaps tied to the foundational software engineering principle that, particularly when you don't know what you're doing, you should plan to write the software at least twice. Throw the first one away because you'll kind of understand the problem after you finish that. I think that one of the things that is very important in this area is to have a clearer discussion of intentionality. I'm very struck, as I mentioned yesterday in one of the discussions, by the value that some of the funding agencies, at least in the States, have gotten out of calling for data management and data sharing plans as part of funding proposals. And what's striking to me about that is that the demand for those is not prescriptive. It doesn't necessarily say you have to manage your data this way or that you have to share all your data. What it says is that you need to think about this and you need to articulate your intentions as part of your proposal, and that those panels that evaluate and rank your proposal will take your analysis of that into consideration in determining what they believe is the quality of your proposal. I think that that is very helpful in the software world as well. Um, when we look at funding that's not specifically targeted at major, a priori infrastructure components, but in fact software in this kind of middle zone. It's interesting to me also how open source seems to be now a working assumption in almost all of our discussions. It was fascinating reading through the papers that were submitted, the position papers. Many of them spoke very strongly to the notion of open source and community source as a way to support various kinds of software. I'm going to return to that set of theories a little later because I think those of us who've been involved in trying to sustain community source efforts have realized that that's really a very complicated and uncertain business, and that indeed many of those community source efforts work specifically because there are institutions that believe that whatever the software project is important enough to them that they earmark competent resources in order to contribute to that effort on an ongoing basis. And I want to, underscore words like earmark and competent in that framing. But I think it's helpful to remember some of the other reasons that open source is important. Open source is not just important so that you can take a lottery ticket on the formation of an open source community. It's also important because it gives people options. If it turns out that nobody else wants this thing, but it's really important to you for whatever reason that it continue, and it's important enough that you're willing to commit the resources to make it happen, you can do that. It basically not only has this community property, but the property that independent actors can sort of reassessment the judgment of communities independently at any given time. That actually turns out to be a property that I think we greatly underestimate in terms of sustainability strategies. It's basically a sort of an insurance option. What it says is that if I'm using this, nobody can just tell me it's discontinued next week. That is actually a big issue with commercial software historically. It's a big issue with all kinds of commercial gear where people just pop up and say, we're withdrawing this from the market because we don't want to support it anymore and we want to drive users to some new product, often in a rather disruptive way. And indeed, in commercial settings, there are often very good reasons why you do that, even though your users hate it. And we can talk about, offline some of the examples of that process and some of the community responses to it. But I think that open source, if nothing else, provides some measure of assurance there. There's another reason, I think, two other reasons why we really should insist on open source and depositive source when software is produced as part of funded grants in most cases. Open source is how we learn about software. One of the best ways to actually learn to do software is to look at other software And we're actually kind of short on examples of software that you can look at across time. We don't make nearly enough use of this, I think, in teaching software engineering and programming. And building up a base of materials that other people can look at and borrow freely from is a very worthwhile thing. The third reason why we want open source ties into, I think, one of the first drivers for this discussion of software sustainability, and it's about reproducibility. In science, we want to be able to reproduce experiments. That's sort of one of the fundamental cultural expectations that we've had ever since various kinds of sciences moved out of the domain of alchemy and into reproducible science. Now, to be sure, we honor that as much in the breach as in practice, but it is a desirable goal, and it's one that has been receiving more attention lately. Being able to get to software, having it as open source, being able to inspect it, being able potentially to rerun it in conjunction with data. And I'll return again later to the data software duality, which we really haven't talked about much at all. That gives you, at least for a window of time, some better hope of reproducibility. I think that window of time and this sort of notion of ease and window of time is very interesting and actually is a property of reproducibility of science generally that we don't much think about. You know, it's much easier to reproduce a result that is of fairly recent vintage. The software is probably still around. It might even run. The experimental methods are relatively current in the field, and even if the methodology is a little less transparent than you might think, you can sometimes find people who can explain it at the lab that announced the results. This gets harder and harder across time. I would speculate trying to reproduce 50-year-old science is actually a good deal more challenging in many ways than reproducing this year or last year's scientific results. Part of reproducibility, by the way, and again, this was mentioned yesterday in several settings, but I think is terrifically important, is this whole question of software provenance, of understanding versioning, configuration management, interdependencies between multiple software packages that make things run, and being able to document that. Being able to say, this result comes out of this version of software, or this set of software, more accurately, at these versions in conjunction with this data. We are much less good about that than we should be. And I think some focus very specifically on that kind of provenance and versioning interdependence and the establishment of more widely understood best practices is very prudent there. I believe it was Brad yesterday that had the courage to speak in public about something that also always terrifies me about software. We tend to talk about software in terms of its usability or its stability. You know, well, this software is crashing all the time, it can't be very good, or I can't really figure out how to use it. The software that scares me the most is the software that's pretty stable but occasionally gives you the wrong answer. And we don't always notice that, especially after we've gotten a certain level of trust in it. And in the same way that when you have, for example, a data falsification and a paper is withdrawn from the literature, and then there's a whole domino effect of other papers that may have built on that that need to be reassessed. We are going to, I guarantee, run into this in software. In fact, we already have on a number of occasions, I believe. We just don't talk about it very much and never have, in part because we've never been able to walk the cat back from these kinds of problems very effectively. I think that to the extent that we are recognizing a fundamental methodological change in the practice of science, it's really incumbent on us to start positioning to deal with these kinds of problems that are inevitably going to occur and get discovered. And part of the solution to this is systems of provenancing and version management. Now let me talk a bit about the other side of sustainability, or another side of sustainability that we're very interested in, and that's reuse as opposed to reproducibility. That's being able to move the software into a different setting, use it again, use it in different communities, doing different things, different communities perhaps doing similar things, and how to facilitate that. I think that when we talk about reuse and sustained use over time, we get into a lot of interesting questions here, and I'm going to just mention a few and how to fit together. One is how much we're focusing on sort of software ecosystems and how much we're concerned about individual software components. What I think is liable to happen is individual software components die, improve, evolve, or are replaced sometimes. But we're increasingly using these in complex arrangements, and we really need to be mindful of the health of the ecosystem and not overly focused on individual small components of that. It seems to me that some of the best facilitators of reuse and of sustainability are things like investments in standards, investments in smart architectures, investments in modularization and factoring. It's striking to me that there has been little investment traditionally from many of the funding agencies in those sorts of things. I think that if we're going to deal with questions of software sustainability, they really need to go hand in hand with investigations into architecture and standards. And I think they need to be investigations that really emphasize the interplay between good standards development, good architecture, and good sustainability. Often, again, these things have worked at odds with each other. There's a certain kind of standards practice which certain players in the industry enjoy a great deal. And indeed, in many areas of standards industry, rapidly became dominant because they put money into it where the research community wouldn't. And that's to come up with these sort of disruptive standards that obsolete installed base every 5 years or 3 years or whatever. That's a wonderful thing. You can sell a new installed base every 3 or 5 years. And frankly, I think sort of cold-eyed assessment says some of those steps from version 1 of a standard to version 2 of a standard, or from one standard to the next, came with tremendously improved function. Others were really fairly dubious, and were as much about obsoleting old things as anything else. I think that we need to take a little more responsibility for that, and part of that is playing a bigger role in those kinds of areas. I'd also suggest that This is a wonderful area for a little more empirical work on software lifecycle, preservation, portability, stability, and things like that. And that those are appropriate areas for some modest amount of investment too. If we think about long-term commitments to developing and fielding and managing sustainable software, it would probably be useful to do this on a data-driven basis, or at least a data-informed basis. Life cycle is a very interesting kind of an issue here. And I'd like to focus for a couple of minutes on the sort of latter parts of the life cycle. We spend a lot of time talking about the early parts of the life cycle and how to move from development to something that's stable enough to put out there and find a community, and then how it matures and gets sustained. It seems to me that one of the biggest problems we've got right now is that things don't sit in a steady and mature state for very long. We just heard numbers that suggested that sort of the shelf life of software that's just left alone is maybe 6 months to a year. That is an astoundingly awful number for the level of investment that we put into these things. And we all know why this happens. Somebody's improved something somewhere or made some gratuitous change to some piece of environmental software upon which this depends or something. But I think we really ought to be doing a kind of a focused effort to try and get that shelf life up a little bit. It's those, in some ways, all of the software, or a great deal of it, is really a necessary evil. It's a tool for helping to do some kind of scholarly work that you're trying to do. And tinkering with the software is really not an end in itself. It is a overhead cost. So the place where you really get the benefit is after the software gets embedded into the scholarly work, and you can get on with the scholarship without having to go with it through a new cycle of software tinkering. The longer we can make that period, the greater the payback on a lot of these software investments. And right now, that period is very short and very problematic. I think we also need to think about, and this is again where open source and the availability of source that can be freely modified actually is very helpful. Long end of life for software, where you put some very minimal maintenance into it for fixing significant bugs or dealing in a minimal kind of a way with keeping it running subject to these annoying environmental changes. There's an amazing amount of commercial software, for example, that just stops at some point because it needs a little fiddling to move to a next version of an operating system, and the commercial vendor has decided they're not going to deal with this problem and disbanded the team that works on the software. But the actual amount of work to keep it alive for another 3 years, very small, if someone could just go in and do it. And we can do that in the open source environment. I think thinking about those sorts of interventions is important. I want to also underscore the issue of archiving software at the end of its life cycle. Making sure that we have the software saved in a useful way on a permanent basis is something we don't do well. We don't understand how to do well. And we ought to really reconsider. I invite you to look at a few of the case studies. These are hard case studies to understand because you really need to allow 10 or 15 years to elapse to get the full joy of it. But we are seeing a few examples of this now. There are people out there who seem to have a lot of time on their hands and are doing interesting things like writing emulators for IBM 360s and 370s that you can run on your laptop in your spare time. Now, having done that, of course, this resurrects the entire question of, well, and what about all the software that ran on that you'd like to run on your emulated IBM 360 on your laptop for, whatever perverse reason? Well, we didn't really do a very good job of saving that in an orderly fashion, interestingly enough. So there are, in fact, a lot of retired systems programmers now who, are rooting around in their garages, finding punch cards and old 9-track tapes. But the most important stuff is actually in their heads and in their reminiscences, because it was really just sort of never documented in an organized way. And I think actually there's a good case study there for somebody to do, but we really ought to learn from that going forward. I also want to suggest that I think we're increasingly getting into a period where having software that runs is not the same as having software that runs well. There's still an awful lot of software that was written primarily for sequential machines or for machines with small numbers of processors. And as we move into this era where scaling up means large numbers of processors, I think that we're going to be facing a great deal of software that, while it runs, doesn't really run very effectively in that environment, and we're going to need to think through what to do about that, or at least try to figure out what to do about that. I think that's going to be a bigger problem than we realize. But I think it puts some stress on this question of, just because things run doesn't necessarily mean they run efficiently, doesn't mean that they scale up well. And often people who develop software and people who use software aren't necessarily well attuned to that distinction. When we talk about long-term sustainability at scale, I think we got some very valuable reminders from the talk we just heard that it's not just about software coding, it's about documentation, it's about education, advocacy, outreach to users and listening to users. It's about support structures. There's a whole set of activities that really have nothing to do or little to do with writing code and debugging code that need to take place in order to have sort of large-scale, growing, active adoption of software in cases where that's our goal. And how to connect those up to development organizations, I think, continues to be a problem. I'd like to underscore, though, one other paradox here that shows up in the sort of open source, community source arrangement. So you get one of these pieces of software. It develops a large base of users, actively engaged, thinking of more things it could do. Now, this is being developed on an open source base. Unfortunately, as we've been reminded a number of times, graduate students, while most of them can code, aren't necessarily good software engineers. There is kind of a distinction between those two things. I mean, most graduate students in the sciences pick up a certain amount of computer programming by the time they get to graduate school. In fact, many of them pick it up by the time they're in high school. But being able to, hack your way through a piece of software to put in some improvements doesn't necessarily mean that this is going to produce a elegant, stable, well-engineered software base over a period of time. We really need to think about how to manage these kind of engaged folk in a community that supports open source. I think we've actually got a tension here that we're kind of trying to have it both ways on, and we really need to think about that. Yesterday, one of the discussions was about saying no, and we may need to actually recognize we need to say no gracefully a lot more often. Or to try and figure out how to, build layers of software and add-ons in various ways, and then re-engineer the add-ons that prove to be really useful from the periphery into the core across time. I don't know exactly what the right answer is there, but I think we need to recognize that we're facing a sort of an ongoing tension and contradiction. Now, two other points I want to make. Open source is a wonderful thing. It's also a very dangerous thing for software authors at a certain level. There's a sort of a paradox in that if you put your code out for inspection, you're inviting people to come after you for everything from software patent infringements to copyright infringements if you've borrowed bits of the code from somewhere. We actually, interestingly enough, have a set of very strong negative motivations in place for making source code available on a large scale. It would probably be useful for some of the folks who are investing in open source cyber infrastructure to recognize that that is a potential problem and start thinking a little bit about what they can do to contribute to the mitigation of that problem. It would seem to me, for example, that if you are simply recording a piece of open source source code someplace that is the outcome of some research effort, that maybe there ought to be some kind of exemption you can operate under where people will not come back and go after you retrospectively just because you've made the code available at the end. That actually is a bigger potential problem than we might realize, because to the extent we move towards mandating open source, it pushes a lot of liability onto individual researchers and onto the institutions that host them in ways that we haven't really thought about. Final set of remarks I want to make. In the last 5, 6 years, there's been a growing focus on the importance of data in e-science. And Chris Greer, who was here yesterday and I don't see today, has actually been one of the leading voices in helping the scientific community and the funding community to think through how to deal with this. Part of the response to this has led to things like the data sharing and data management plans that I talked about a few minutes ago that are now increasingly part of the documentation that's expected with funding proposals. I think that there's a tremendous amount that we can learn in thinking about managing software as an asset that comes out of funded research and that has value beyond the duration of the initial grant, from looking at the same kinds of conversations around data. I think the data folks are in some ways a bit ahead of the software world on this, and that there's a lot to be learned. I also think, though, that there's a pretty close coupling in many cases between software and data. And I'm a little worried about the notion that we develop two completely independent streams for thinking about how to manage this. Because when we look at a lot of the experimental data, that is now increasingly being preserved and managed and having life cycle thinking done about it. That data is very difficult to interpret without the relevant software. You can talk all you want about documenting it, but in fact, often the best documentation for it is the software that processes it, especially if that software is well written and well commented. I think that we need to look at strategies for, at the very least, connecting the thinking about software sustainability and about the life cycle and management of research data rather than treating these as independent kinds of questions. And I think that this is an area that would benefit not only from some sustained conversation between the people working in each area, but in fact, again, from a certain amount of empirical research, which I would urge the folks who are investing in the construction of our ongoing cyber infrastructure frameworks to think about how they can advance the conduct of. That question of software and data linkage is one that I think is very difficult. It is going to be very different in different disciplines, and I think that we need to be very wary about having the discussion on a discipline-independent basis as sort of a one-size-fits-all. Some of it ties very closely to questions about experimental or observational apparatus and how that is characterized discipline to discipline, how much implicit and how much explicit documentation is made of that. But I think that this is one of the sort of fundamental areas of focus that we need to be looking at, both in terms of software sustainability and indeed part of the case for software sustainability, as well as in terms of data management and the facilitation of data reuse. So I hope these are a few useful things to think about, and I'm ready for questions, and I've got one teed up right here.
Cliff, you were talking about the disconnect between software and data over time. I mean, we see that today. We don't need to wait till tomorrow, right? This is occurring all the time. Every faculty member's research that they're requesting retention on, they check the box that isn't on the form that says forever, and then expect magnetic tape or other media to still be available to retrieve it. But there are changes around the ecosystem. Think about virtualization and the ability to capture an entire environment and the data sets as a single artifact that potentially could then be quite useful over time. But if we continue to grab these as separate, distinct chunks and then try to recompile the operating environments, the software, the tool sets, and the data, then I think we have a multi-level problem. So are you seeing any trends or transitions that are happening there?
I'm not seeing nearly as much attention to that as I'd like to, and that's one of the reasons I'm making the suggestion that we need to start considering the software and data together in a more holistic way when we think about preserving research results for reuse or reproduction later. Things like virtualization look very promising in some ways, but again, they require, I think, that we get a better handle on some of the software provenancing so that we actually can be explicit about what that configuration was that we want to preserve to drop back into a virtualized environment. And, truth be told, there are some situations where I think we're probably going to need to go to something as heavy-handed as those virtualized environments. There are other cases where I think scientific communities are moving fairly fast on data interchange standards that actually give you a much more managed and documented kind of a way to start separating software from data at scale. So I think it varies a great deal. I think that in some ways, the virtualization feels a little bit like the worst case solution to me, but one that we need to be prepared to exercise when necessary. I think part of the problem right now is we don't really have. Question was, should peer-reviewed articles be accepted for publication when they're missing the metadata for reproducibility? That's obviously going to be a policy choice that different journals are going to make it in different areas. But I can tell you that some of the particularly the most influential journals are starting to get a good deal nastier about that. There's quite a striking report that goes back to 2006 when Don Kennedy was still the editor-in-chief at Science magazine. There was one of these periodic eruptions, where it turned out that somebody had falsified a bunch of data, and it wasn't just one article. I mean, this person had built like a whole edifice on it, and it was terribly embarrassing to unravel it. So he convened a little external group to advise science about what they should be doing to avoid this kind of embarrassment in the future. And that report actually called for some pretty hardline practices to be applied, at least when the editors felt it was necessary. When you get a result like the latest cold fusion thing that really surprises everybody, they suggested that the editors actually sit on it until and require the submitters of the article to cooperate with another lab to reproduce prior to publication. So that's really sort of the ultimate strong barrier. You say, I'm not even going to publish your result until we can get it independently verified. And that was a very rare thing for a long time outside of mathematics, where the reviewer really can kind of re-verify the proof, if you will. I don't know how often that's happening, but one does hear tell of it happening occasionally. Personally, I think that we are seeing a lot more emphasis on reproducibility. One of the things that I think has been very powerful is the emergence of videos to supplement the methods section on experimental work, for instance. But I think software and data are both critical parts of that reproducibility.
I mean, I think it is related to what's going on here. There seems to be some kind of a conflict between keeping the data open versus keeping the data proprietary. I mean, there is some, for example, some issue between NIH, which wants all the data open, and CAS, which is the Chemical Abstract Service, which is a commercial organization which sells the data. So there is, I mean, if one sees that there is value to a data which can be marketed, then it may not be as open as one would wish. And the other point is, I think the funding agencies are not clearly stating how the data has to be kept open. Can you comment on those things?
Yes, I can comment on both of those things. The first point, certainly it's true that there is data with considerable commercial value, and there's all kinds of negotiating that goes on about that. It's a very complicated area that doesn't lend itself to really simple solutions, especially when you've got these kind of funny mixtures of data and potential patents, for example, for pharmaceutical things that the university and the researcher would like to license out under Bayh-Dole for technology transfer and to bring revenue in. And I don't think there are, sort of sweeping generalities I can give you there. I do think, though, that one of that there are a couple things worth identifying. One is that funders are getting more aware that and recognizing more explicitly that data is an asset that comes out of the research process. They are starting to ask for more clarity about how it's being shared and how it's being preserved. Some of them are also getting a lot more prescriptive about how they expect it to be shared. It's striking, for example, that some of these foundations that that fund research on specific diseases are starting to develop very aggressive data sharing policies, at least within the groups of researchers that they fund. There are some of the federal funding programs and private funding programs require data to be publicly available within a certain time period, and there's all kinds of specific disciplinary and agency kind of deals and norms about how long an investigator gets to exploit the data solely, and then when it has to be public. So, for example, for planetary data, typically I believe the PI and his or her team get 2 years on it, and then it becomes public. But there's a lot of variation from field to field. I think there is a growing sense, and part of that is I think implicit in the NIH deposit mandate, that the products of federally funded research ought to be broadly available. And right now that has, as on a policy basis, been somewhat more explicit around publication than data, but I think you'll see that change over the next decade. The last thing I'd just underscore, though, is that there's also this whole sort of opposing theme that's showing up around human subjects data. We have become, at least in the United States, ever more encompassing in what we consider to be human subjects data, and that requires the involvement of IRBs, talking to random people on the street or looking out the window or things like that, and recording what you see are in some institutions now starting to get characterized as human subjects research. So you've got a big problem whenever you talk about the sharing of human subjects observational data and the various privacy and informed consent things you need there. So it is worth just noting that sort of tension that's also emerging.
So back to open source as I guess the underlying assumption as being able to save how we're getting to sustainability. Right now, the open ecosystem from the Linux stack up, the development moves extremely fast. I mean, the 6-month timescale really is their timescale for releases for a lot of the stack, and that's actually in sort of conflict with what the science community needs to some extent, right? I mean, you're talking about having access to codes as long as the data sets are available, some sort of lifetime that's clearly multi-year. But at the same time, we're talking about codes that tend to get produced and then sort of stagnate. And and the codes are fine, but what happens is things move under them, right? But I'm not sure people are talking about how to use open source or the qualities of open source to allow scientists to build a more stable platform. You might not be able to rely on things that are coming out as they come out. You might have to make the investment at a high level to define a platform and then put the man hours in to keep it stable. And that's going to cost. You can't what you can get for free is rapid development, because that's what the developers from the Linux kernel on up are very interested in. They're not so interested in keeping things stable. It's not
That's right.
what the projects are defined as. And so if that's a high value need for the science community, then that needs to be accepted early on and priced in, because it will take work
Yes.
to, as you drag away from the upstream trunks of each code base, it's going to take more and more effort to keep things maintained for your uses. So I'm not sure people have really said that. So I want to.
Yeah, I mean, I think that's absolutely true. The stress is very often on rapid development, new features, exploring interesting new stuff, supporting new hardware platforms, all that kind of thing. It is very boring to write backwards compatibility code and to support installed bases. And it may be that one of the things that we need to do for the scholarly community as the price of poker is to make some investment into some of these open source communities, specifically to deal with some of that back compatibility stuff that tends to be boring for a lot of people.
Yeah. Yeah, my experience is that they're not necessarily unwilling to do it. I mean, to have someone do it and add
Yeah.
backward compatibility, it's a matter of the people who value it aren't the people participating.
That's right.
And if the science community values it, then you'll have to find a way to price in
Yeah.
putting effort into those projects that you are relying on to build up.
Yeah, it's not so much they, are opposed to seeing it. They just, this is not an exciting thing for many programmers to work on. It's right up there with error recovery code or diagnostics. But you need all three of those actually. It's also, interesting to think about the commercial market here. The commercial market is very schizophrenic about backwards compatibility code. They don't want to do it often because they can sell more stuff, but they get a lot of pressure from their installed bases to recognize that they have to do it. And as the installed bases get bigger and bigger, that pressure gets more severe. But this is a place where, I can imagine, for example, the science agencies that are concerned with sustainable cyber infrastructure might want to get together and have an ongoing conversation with the platform developers of the key software that they rely on about back compatibility and where the pain points are going to be and what